Yesterday, Apple shipped its first 2nm chip. Then it invented a brand new CPU core tier. Then it glued 4 dies together and called it a desktop. August 25th, 2026. Apple's newsroom posts the launch of M6 and M5 Ultra, debuting in the new Mac Mini and the new Mac Studio. Sri Santhanam, Apple's VP of Silicon Engineering, calls it the next giant leap in performance and AI compute for Apple Silicon. And buried in a press release full of percentage signs is the most interesting number in consumer computing right now, 1.2 terabytes per second. Let's start with M6, because it's the one most of you will actually buy. 2nm process. That's the leading edge. More transistors in a smaller die, which is the entire reason this chip gets to be faster and cooler at the same time. 12 CPU cores, which is 2 more than M5. 12 GPU cores, also 2 more than M5. And a dual 16-core neural engine that Apple says delivers up to 2 times the peak compute of the previous generation. But look at how those 12 CPU cores break down. Because Apple quietly changed the recipe. It's not 6 performance and 6 efficiency. It's 2 supercores, 4 performance cores, and 6 efficiency cores. Supercores, that's a new tier that did not exist in the M series lineup a week ago, and Apple introduced it with roughly the same fanfare you'd use to announce a new shade of aluminum. Here's what that actually means, because it's not marketing. Single-threaded performance and multi-threaded performance want opposite things from a chip. A single fast thread wants an enormous core, deep reorder buffers, wide decode, huge caches, and a voltage curve that will happily burn power to shave nanoseconds. Multi-threaded throughput wants the opposite. Lots of smaller cores sitting at the efficient part of the curve because performance per watt collapses at the top of the frequency range. 2 tiers used to be enough. Now Apple's saying 2 isn't enough. So the 2 supercores blaze through single-threaded work. Apple claims the world's fastest CPU core. The 4 performance cores use less power and gang up with the supercores when you throw a real multi-threaded job at it. And the 6 efficiency cores handle background tasks like file indexing. The result? Up to 1.2 times faster multi-threaded than M5. And up to 2.4 times faster than M1. Apple specifically calls out compiling code and running agentic AI workloads, which is a sentence that would have been science fiction in a chip press release 3 years ago and is now just a bullet point. On the graphics side, each of the 12 GPU cores gets a Neural Accelerator. Apple says that's nearly a 30% increase in peak GPU compute for AI compared to M5 and more than 8 times M1. And it specifically ties that to faster prompt processing when you're talking to an on-device LLM. Hold on to that phrase, prompt processing. We're coming back to it, because it is doing a lot of quiet work in that sentence. And then there's M5 Ultra, which is where the story stops being about transistors and starts being about adhesive. Here's the backstory in 3 sentences. Chips are printed by shining light through a mask onto silicon, and that mask has a hard physical size limit. You cannot print a single die larger than roughly the size of a postage stamp, no matter how much money you have. Worse, defects are random and roughly uniform across a wafer, so the bigger your die, the more likely any given copy of it lands on a defect and goes in the bin. So when you hit that wall, you stop making one big chip and you start making several smaller ones and wiring them together at absurd speed. Apple has been doing this since M1 Ultra in 2022, using a silicon bridge it calls UltraFusion to stitch 2 dies into one logical chip that macOS sees as a single processor. M5 Ultra is the first quad-die architecture in an M-series SoC. And the way Apple got there is genuinely funny. It took 2 M5 Max chips, which are themselves already dual-die parts, and fused those together. 4 dies, 2 glued-together chips, glued to 2 more glued-together chips. The inter-die fabric runs at 4.4 terabytes per second, which is the number that lets the operating system pretend none of this is happening. The totals up to a 36-core CPU, up to an 80-core GPU, and 1.2 terabytes per second of unified memory bandwidth, 50% more than M3 Ultra. Do the division, and each of those 4 dies is carrying 9 CPU cores and 20 GPU cores. The GPU now has neural accelerators too, which M3 Ultra did not. Now, the one concept worth actually understanding here, because it explains every purchasing decision you're about to make. When an LLM generates text, it produces 1 token at a time, and to produce each token, it has to read essentially every weight in the model out of memory, not compute on them cleverly. Read them. So your generation speed has a hard physical ceiling, and the formula is embarrassingly simple. Tokens per second is roughly memory bandwidth divided by the number of bytes of weights you read per token. That's it. That's the whole thing. Run it. A 70 billion parameter model quantized to 4 bits is about 35 gigabytes of weights. On M5 Ultra's 1.2 terabytes per second, that's a theoretical ceiling around 34 tokens per second. Call it low 20s in the real world, once you account for attention overhead, and the fact that no memory system ever hits its rated number. That is a genuinely usable local assistant, running a frontier-class open-weight model on a desktop with no API key and no data leaving the room. This is also why the GPU core count matters less than you think for chat and more than you think for everything else. Generating tokens is bandwidth bound. Your 80 GPU cores are mostly sitting there waiting for memory. But processing your prompt is compute bound because the whole prompt goes through in parallel and there's actual math to do. That's the split. GPU compute decides how fast it reads your 40,000 token codebase. Memory bandwidth decides how fast it talks back. Apple's marketing is precisely correct that neural accelerators speed up prompt processing. It's just not the number that decides whether the model is fun to use. So, the skeptical part. Apple describes M6 as being for everyday users, students, developers, AI hobbyists, and enterprises. AI hobbyists. Let's take that seriously for a second. M6 gives you up to 170 gigabytes per second of unified memory bandwidth and up to 32 gigabytes of unified memory. Run the same formula. An 8 billion parameter model at 4 bits is about 4.5 gigabytes. So 170 divided by that is roughly 37 tokens per second, ceiling, before reality takes its cut. That's fine. That's a good local coding assistant. But that 32 gigabyte ceiling is not a soft limit. It's a wall. That 4-bit 70B model needs about 35 gigabytes of weights. It does not fit. Not slowly at all. And the memory is unified, which is the M series' greatest strength, and at 32 gigabytes, its most annoying constraint, because macOS, your browser with 40 tabs, and your actual editor are all eating from the same plate. The bandwidth bump from M5 is roughly 10%. The capacity story is the one that didn't move, which sets up the punchline of the entire launch. Apple's whole strategic pitch is private, on-device AI. The model runs on your machine. Your data stays on your machine. And the spec sheet quietly says, yes, absolutely, as long as your machine is the Mac Studio. The Mac Mini is a wonderful computer that will run small models very pleasantly. The Mac that runs the models? The marketing is actually gesturing at costs Mac Studio money. Second thing, the press release isn't advertising. Every performance figure in it is a ratio. 2 times the neural engine peak compute, nearly 30% more GPU AI compute, 1.2 times multi-threaded, 2.4 times M1. 2 times what in what unit? There is no tops figure, no flops figure, no absolute anywhere in the performance claims. The absolute numbers Apple does publish are the ones it's proud of and can't fudge. 170 gigabytes per second, 1.2 terabytes per second, 4.4 terabytes per second, core counts. Ratios are for the parts where the baseline is doing the heavy lifting. And third, the dual 16-core neural engine is a real impressive piece of silicon that most of you will never point an LLM at. The popular local inference stacks target the GPU through metal, not the neural engine, because the ANE is built for fixed, ahead-of-time compiled model graphs and not for the ragged, dynamically shaped decoding loop of a chatbot. Apple says system frameworks can automatically use both engines simultaneously, which is great for the models Apple ships. Your Llama running at 4-bit is talking to the GPU. So what should a developer actually take from this? Buy for bandwidth and capacity, in that order, and treat CPU core count as almost irrelevant to your inference decision. If the largest model you'll ever run is in the 8 to 14 billion range, the M6 Mini is arguably the best performance per dollar local AI box on the market. If you want to hold a 70B in memory and stop paying rent to a GPU cloud, the quad die is not a luxury, it's the requirement. And keep the comparison honest. 1.2 terabytes per second is roughly a third of what an H100 pulls from its HBM stack. Apple didn't beat the data center. It got close enough that for a lot of workloads, driving there stopped being worth it. The real story here isn't the 2-nanometer process. It's that the industry's answer to, we can't make one chip bigger is now, officially, so make 4 and bolt them together at 4.4 terabytes per second. Every serious vendor is doing some version of this. Apple just did it twice, recursively, and put it in a box you can carry. Moore's Law didn't die, it just got laminated.